Okay, in this video I'm going to begin exercise 5C of the book Fundamental Applied Mathematics. We're on page 139 and the question is 1. It reads: a particle of mass 10 kilograms is pulled over horizontal ground. The pulling force has magnitude 100 newtons and makes an angle A with the horizontal, where tan A is equal to 3/4. Find the normal reaction and the acceleration, first of all, if the ground is smooth. Now, this question is actually quite tricky, and it definitely does test your knowledge of Newton's second law. Not necessarily Newton's third, but definitely Newton's second law. And I suppose Newton's first law too. Now the first thing I've done is I have resolved the pulling vector. You have to make the two vectors which when added together create it, and these vectors must be parallel to the axes or the I hat and j hat unit vectors. So we have that vector there, and just to write it explicitly, the pulling vector is equal to p sub x I hat plus p sub y j. Alright? So we know, of course, that tan A is equal to 3/4, so we're able to get the sine and cosine of A. So this is going to be p times the cosine of A I hat plus p times the sine of A j. Alright, so look, I'll leave the working out of that to you, and let's put in the answer straight out. So it works out as 80I plus 60j, which makes perfect sense because it is in the first quadrant, and we know it's in the first quadrant. Alright, so it's plus I plus j, that's correct. Now, the next thing we need to do is to work out Newton's second law, how it applies. So if you look at this, right, we have a force going in the positive I, positive j direction, or the first quadrant. Now, is there any reason for us to assume that the acceleration isn't pointing in that direction? In other words, the acceleration doesn't have a y component or doesn't have an x component. I think that it should have. In general it should have, and that is absolutely true. However, you need to read the question carefully. It says it is pulled over horizontal ground, and that implies, poorly I think, because it's phrased poorly, but that implies that it doesn't actually get lifted from the ground. Alright, that's very important. So if it doesn't get lifted from the ground, well then the sum of the forces in the y direction are equal to 0, because it is not accelerating in any particular direction. Alright, so that's highly important. We'll demonstrate that in a moment. So first of all, let's go back to Newton's second law, which says that sum of the forces is equal to the mass times the acceleration. So let's do the x direction, or the I hat unit vector direction first. So we're going to get that it's going to be p sub x I hat is equal to the mass, which is 10 times a sub x I hat. And you're going to get that the acceleration is equal to 8 I hat. Alright? Now, that's the acceleration in the x direction. Alright, that's perfect. That's perfectly correct, and that's the right way to go about getting that. Now, the next thing we need to do is work out what the acceleration in the j is. And we've just said that since the sum of the forces around the y direction is equal to 0, and we know that's equal to the mass times the acceleration, well, we know the mass is non-zero, therefore the acceleration is equal to 0. A sub y in the j hat direction is equal to 0. So we can say, of course, that the acceleration vector is equal to 8 I hat plus 0j. That's very important. It took me a while to kind of cut that, mainly because of the way the question is phrased, but that's kind of beside the point. So let's go ahead and apply this new knowledge that the sum of the forces is equal to 0. So the sum of the forces in the y direction are equal to the normal vector plus p sub y minus the weight vector, or I could say plus the weight vector. It doesn't really matter, but in this case, yeah, plus the weight vector, excuse me, that's correct. Alright, and they are equal to 0. So let's plug in what we know. We know n, it's plus n sub n j hat plus 60 j hat minus, that turns out there, we'll say 98 j hat is equal to 0. Therefore we can say that n is equal to 98 minus 60. Alright, so it turns out, of course, to be 38 in the j hat direction. Alright. Now an important thing to look at here is, not 30, 38. So an important thing to look at here is to kind of say, well, does this make sense? Does it make sense to say that the normal vector is 38 units in the j hat direction, whereas the weight vector is 98 units in the negative j direction? So in this case, the weight vector is not equal in magnitude to the normal vector. Is that true? But surely these should be action-reaction pairs, equal but opposite sort of thing. And the answer is they are. However, in this case we have an extra force in the j direction. So it's not just usually W is equal to n. Down we have an extra force, so it's not the case. And this would be like in an elevator. If you think about it, in an elevator, because you're accelerating upwards or downwards, your weight or your normal vector changes, and that's what's happening in this case. Alright, so the next part of the question says, what happens if the ground is rough with a coefficient of friction of 1/2? Alright, a coefficient of friction of 1/2. So let's just add our coefficient of friction. We're going to get rid of this acceleration vector, in fact. We don't really need that. I'm assuming you understand that at this stage. So the frictional vector is going to be this way. Fr is equal to the normal force times the coefficient of friction mu. Alright, and of course it's going to be in a negative I hat direction. So I probably should write it this way, that the frictional force is equal to the normal force times mu in the negative I hat direction. Alright, so let's go ahead and work that out. So the normal force we worked out as being 38 units. And that won't change because just because we've added friction, which is just in the I would say the I hat unit vector direction. So it's not going to affect the normal force. So we can say that the frictional force is equal to 38 units times the coefficient of friction, which we're given as a half. We know it's in the negative I hat direction. Alright, so what's that? 19 units, isn't it? So we get negative 19 units in the I hat direction. Alright, that's pretty straightforward. Alright, so what else can we do? So we know that we have negative 19 units in the I hat direction here. Alright, so what are we asked to find out? The acceleration and the normal reaction. Alright, so the first thing I'm going to work out is the acceleration. So let's just apply the same concepts which we've already applied, such that the sum of the forces in the x direction in the I hat unit vector direction is equal to the mass times the acceleration in the x I hat. So we're going to get the following. We're going to get p sub x, which was 80 I hat, negative 19 I hat, is equal to the mass, which is 10, times its acceleration in the I hat. Alright, so what's that? 61. 61 I hat is equal to 10a I hat. Therefore the acceleration in the I hat direction is equal to 6.1 I hat. Alright, so that was pretty straightforward. 6.1 is correct. So we know, of course, for the same reasons we said in the past, that the acceleration vector in the j direction is equal to 0. So next, let's just get the normal force. But there's no need to get the normal force because, as I've said already, nothing else will change. We've only introduced a frictional force, which is only in the I hat unit vector direction, and thus it doesn't affect it. And as I said a moment ago, the normal vector now will not change, and it's equal to 38 units in the positive j direction. Alright, so I think conceptually, I think this question is quite difficult. If you understand this, you're doing quite well, in my opinion. So thanks for watching. Please pass it on to your friends and subscribe to my channel.